Hello, welcome to our demo, On-the-Fly Data Transformation in Action. Before we move to the demonstration scenarios, let me introduce relational memory. Relational memory is a novel hardware designed for data transformation as an answer to the question of how can we access only the desired columns without storing or maintaining multiple copies of data. Relational memory can be implemented in commercially available PSPL platforms such as Xilinx Autoscale, Engine, and Intel Azure. These platforms are equipped with programmable logic tightly coupled with the traditional processing system. Programmable logic, or FPGA, consists of programmable interconnects and configurable logic blocks, thus any hardware logic can be programmed on it. The relational memory engine is a specialized hardware for vertical partitioning on the fly. In other words, a relational memory engine transforms the data from the base row store to the column store with only desired columns, or to the hybrid layout of columns and rows depending on the query. From now on, I'm going to explain how relational memory works and how to use it. Let's start with how to use relational memory engine. As a simple lightweight abstraction to use the relational memory, an ephemeral variable is proposed. Unlike regular variable that leads to memory access, an ephemeral variable is a special type of variable that is mapped to a fake address that CPU thinks exists. Whenever CPU tries to read the data from the ephemeral variable, the read requests are intercepted by relational memory engine. Ephemeral variable identifies the specific subset of columns to access. For example, if the query requires only 3 fields out of 5, then the ephemeral variable points to an optimal layout that contains only these 3 desired columns. However, it is not instantiated in the memory since ephemeral variable is mapped to a fake address. Instead, upon accessing such a variable, the underlying machinery is set in motion and generates an on-the-fly projection. It provides the reorganized data. In this way, ephemeral variable points to an optimal layout for any query, and the software does not need to consider the underlying hardware and access the data as if its optimal layout is always available. Now I'm going to move to how to build such a machinery. Relational memory engine sits on the programmable logic between the CPU and memory. There are 4 major components: trapper, monitor bypass, requester, and fetch unit. First, trapper is the interface between CPU and the relational memory engine, and it intercepts the CPU-oriented memory request to ephemeral variable. Monitor bypass monitors the completion and availability status of the reorganized data. Requester orchestrates accesses to main memory using DB geometry. Fetch unit retrieves the data from memory. In this example, the parts with colors are the desired columns, and the geo-padded parts are useless data. First, requester gets DB geometry about the base table and what are the desired columns. Then trapper intercepts the read access towards the ephemeral variable. Then trapper notifies the monitor bypass to check the data is available. The monitor bypass checks the corresponding metadata to check the availability. When the data is not in the buffer, monitor bypass notifies the requester about the missing data. Requester issues descriptors that indicates where to fetch the data from the memory and where the useful data locates. The fetch unit fires the read request towards the DRAM. Then fetch unit retrieves the bus lines indicated by the descriptors, and the column extractor inside the fetch unit extracts the relevant parts. The extracted data is stored in the buffer, and the metadata for that cache line is updated. As a result, the CPU can see the table with only the desired columns. When the data is already in the data buffer, monitor bypass knows the requested data is ready by checking the metadata and notifies the trapper, and trapper transfers the data to the CPU. The entire process is automatically handled by the relation memory engine itself. CPU only sees the ephemeral variable. Before we introduce the demo scenarios, let me introduce Xilinx Zynq UltraScale Plus platform, which is equipped with a traditional processing system and programmable logic. In this chip underneath the fan, there are 4 ARM Cortex-A53 cores and the programmable logic, often termed FPGA. There is also 4 GB DDR4 memory on the board. The SD card in this slide contains the bitstream with the relational memory engine inside and the Petal Linux as operating system. In short, this SD card is our storage device. There are also Ethernet port and serial ports, so it is possible to connect the system to the internet or UART serial port. When the power is on, the bitstream is loaded from SD card to FPGA to configure the specialized hardware. When it is ready, the status LED turns to green, then the Linux booting starts. It is the demonstration setup using terminal via UART. When the Petal Linux is loaded, it is possible to use C and C++ codes and bash scripts to test the underlying relational memory engine. We choose a synthetic benchmark to demonstrate the usage of relational memory on the various success patterns as shown in these 4 template queries. We introduce 4 demonstration scenarios that highlights the various functionality of relational memory engine and the impact of various parameters. We provide web-based interface using Jupyter Notebook as shown here. The conference participants can explore demo scenarios while modifying various parameters of queries. There are 4 tabs that users can explore. First 3 tabs is for users to create their own queries from the 4 benchmarks from earlier slides. First tab is to run Q1 that calculates the average of a single column. The left-hand side of the page is to populate the base table. The users can create their own table by modifying the number of rows in the table, the size of each column, and the number of columns in each row. And they can also select the column that they want to use. When the user pushes the execute button, then the command to run the query is sent to the CPU on the target platform and runs the query there. When the query is done, the execution time spent on the query is plotted. The second tab is for Q1 and Q3, which are for simple projection and selection at the same time. Similarly, the left-hand side is to populate the table. Users can modify the base table as they want, and they can choose the sets of columns to project. When the user pushes the execution button, the execution time spent on the query is plotted. Also, users can add conditions as well. We can observe that the relational memory shows the efficient query performance by offering the optimal layout for any query. The next query is the join over 2 tables. Here, users can configure the second table as well as the columns to join from 2 tables. The relational memory accelerates queries over multiple tables as shown here. The last step is to show the performance comparison of 4 predefined scenarios. First scenario is to measure the access overhead towards the relational memory engine that locates on the slower programmable logic. As you can see, the relational memory hot case shows the better performance than the RME cold case a bit, but the access overhead is quite small. So in all other scenarios, we only compare the cold case. The second scenario is to show the MVCC capability of relational memory engine. The first figure on the top shows the normalized execution time while increasing the number of columns to project with no MVCC. The second figure runs the same experiments with MVCC. Since the relational memory can project the valid rows only, the performance of relational memory even gets better. The third scenario is to evaluate the scalability of the relational memory engine. Since the relational memory engine uses the 2 MB of data buffer to minimize the speed gap of fast CPU and slower programmable logic. Thus, whenever the buffer is full, the relational memory engine flushes the buffer and starts to refill them again. As you can see, this buffer flush does not have any impact on the performance, and thus relational memory engine can accelerate queries on the much larger table than its buffer. The last scenario is for join over 2 tables. The relational memory focuses only on the data transformation. Thus, the computational heavy operations such as hash join, the performance improvement is less obvious. However, when we divide the time spent on the computation and data movement, the relational memory can reduce the data movement over than 40%. As shown so far, relational memory, every query always access to the optimal layout. Thank you for your attention.